Good morning, everyone, and welcome back to our online lecture. Today, this course is going to be for 400 level students from Yobe State University, Damaturu, and is assigned as an elective course for our students. And it is part of the requirement for graduation for all the students to consider taking one or two elective courses in the course of their registration. So today, I'm happy I'm part of this plasma physics, and we are going to open an official chapter in order to introduce the concepts of plasma physics. You sometimes heard about plasma as referred as the fourth state of matter, right? But today, in this lecture, we want to look very deep and understand what actually defines a plasma from physical standpoint. We have been hearing that plasma is the fourth state of matter, and it is in a form of ionized gas. So detail of all this will come up in the course of delivering this lecture. Okay? Now, but before then, it is very important for us to look into the roadmap, the course content for this particular course. When we say roadmap, our direction and all the aspect we are going to touch in the course of delivering this lecture. However, you remember I have sent some materials in the soft copy, in the form of soft copy to the group, and also I sent the current slides to the students so that they can read ahead before our physical or online lecture. So I'll be happy for all of you to follow it up and report any area of difficulty to me so that we can explain further. All right. So our journey starts right at the particle level. Here we are talking about the particle dynamics. If you look at the course content, in this area, we are going to study and analyze the motion of charged particles in electromagnetic fields. And we have some very basic questions that we need to answer while explaining this area. For instance, if we ask how do electrons and ions behave when subjected to electric and magnetic forces? So, motion of charged particles in electric and magnetic field is an area of interest, and we are expected to dive deep into this area and clear some of our some kind of doubt we have with regard to this aspect. Number two, very quickly, we are going to talk about the kinetics and continuum description. So in this aspect, from individual particles, we are going to build a kind of statistical and kinetic models to explain or to describe these individual particles, and we will dive into some equations like the Love equation, electron conductivity, and mobility. We will drive the fundamental continuum and diffusion equation under this kinetic and quantum description. Next, we are going to look into plasma waves and transport. In this area, we'll explore the collective behavior and wave propagation, either in parallel or perpendicular to the magnetic fields, or longitudinal waves and linearized magnetohydrodynamics equations. We will also examine the statistical mechanics through the Boltzmann's and Fokker-Planck's equation. Okay, we are going to look briefly into lambda damping and the transport coefficients. And finally, we'll look into radiation and devices to study the kind of radiation in the form of plasmas and the transition, into practical applications related to engineering and also the kind of transformation in fusion reactors like Tokamak's concept. Okay, and at the end, finally, we'll look into some applications, I mean, real world phenomena with regard to plasma. So, in the case of this explanation, it is good to challenge our understanding on maybe why do we care so much about plasmas? Yeah, okay, or the entire aspect of plasma physics. Why are we interested? Okay, so one reason is that because plasma makes up about 99% of the visible universe we are living in. So if we look at the particle motion and the waves, it will guide us towards understanding the microscopic particles trajectory and the waves phenomena that forms the bedrock of controlling plasma. If we move into aspect of space physics and magnetospheres, the interaction between solar winds, the Earth's magnetic fields that creates our magnetosphere, and a kind of a production of the natural phenomena like aurora. Okay, all these can be interpreted with regard to the conceptual phenomena that are taking place in plasma. Okay, and if you talk about the fusion reactors, in fusion reactors, the technological side of plasma holds the key to almost, the unlimited power through the controlled nuclear fusion. Okay, so with this kind of interesting areas, we must have a better or clear understanding of the entire concept of plasma before anything else. Okay, so left me alone. Plasma physics is not just an abstract theory. It is about powering the universe, understanding the universe, and enriching the modern technologies we are handling in our societies. Okay, so uh, from the first slides is just a kind of roadmap, as I mentioned, to explore the physics of ionized matter and from fundamental down to some areas or advanced application areas. All right. So let's start with the first slide, very brief. I decided to make it in the form of slides so that it looks like a summary instead of reading the bold keynotes we have submitted to the class. But through this shortcut, we can understand the conceptual terms, theories, and definitions with regard to the plasma physics. So in the introductory aspect, actually, we introduce the definitions based on the properties of plasma, and we took some parameters from the fundamental, terms, and also touched a very small area of history to understand or to refresh our minds with the fact that this is a long-term area that have been in existence for a quite long time, and it is based on the contributions of many scientists that came to explore the universe. All right. So, uh, plasma, as we explained, uh, is an ionized gas consisting of positive ions, electrons, and neutral particles. It is electrically conductive and responds collectively to electric and magnetic field. All right, so let's start refreshing our minds with the basic thermal physics. Okay, I'll give you an example. When we heat a solid, what happened to the solid? Usually the solid melts into liquids. Am I right? So again, if that liquid is being subjected to further heat, you know, it turns into gas, right? But at that stage, from solid to liquid and down to gas, what happens if we keep adding energy to that gas? All right, this is very important question. So eventually, the thermal kinetic energy becomes large. Large enough to strip electrons away from the atomic nuclei. So this process, ionization, creates a gas mixture that composed of positive ions, free electrons, and the neutral particles. So this leads us to fundamental definitions that plasma is an ionized gas that is electrically conductive and respond collectively to electric and magnetic fields. Take this as the bedrock, as the contextual definition of plasma. One is an ionized gas. It is electrically conductive and respond to electric and magnetic fields. All right. So what we mean by collective response? It is not just a collection of charged particles bouncing around independently. No, there are long-range Coulomb force, force them to act together as a single dynamic system. We talk about Coulomb's law, if you recall, in our previous lectures. Okay, so that force will force them to act as a single dynamic system. This is very interesting area. So it's not just wobbling and bouncing of these charged particles within a confined space. No, there is a long-range Coulomb force interaction that subjected them to act as a single dynamic system. All right. So this is by definition. And then looking at the history, very brief, um, you know, because at this important stage, we need to know how did we get there based on history. As I mentioned, the contribution of other people, happened before even we get to know what plasma is, from the discovery to experimental and down to some applications. All right. So in 1879, Sir William Crookes first discovered cathode rays and then referred to them as what? Radiant matter. Subsequently, in 1970, J.J. Thomson isolated the electrons. Then, later on, an American chemist and physicist, Langmuir, coined the term plasma, by drawing an analogy to blood plasmas, because of how this ionized medium carries electrons and ions. And subsequently, in the 50s, there is a research that was conducted and shifted from a simple gas discharge tubes into a distinct discipline by space observation and early nuclear fusion research. So all these are based on contributions of many scientists that have played a key role in this area. So, however, now, how do we describe plasma quantitatively? As I mentioned in my previous lectures, we in physics, we normally deal with parameters for quantification and the description of natural or a kind of a descriptive phenomena. So similarly here, we describe plasma quantitatively. We rely on several, parameters, for instance, like the number density, temperature in Kelvin, or electron pressure, as well as partial and temporal scale like the Debye length and the plasma frequency, which we will drive in details or in the subsequent lecture. All right. So, with regard to the degree of ionization, a critical quantity to keep in mind is the degree of ionization. In symbol is alpha, the number of ionized particles over the total number of the particles multiplied by 100%. So if alpha is low, we call it a weakly ionized plasma. Some examples include standard candle flames, or just a fluorescent neon, we have been using in our day-to-day activities. However, the second case, if alpha approaches 100%, we have a strongly ionized plasma. So such a high temperature lightning channels or the core of fusion in a tokamak is one of the strongly ionized plasmas. Okay, so we have to remember plasma physics studies how ionized gases interact in some way with the electromagnetic fields. These fields, underpins everything from understanding our sun and space plasma to modern semiconducting manufacturing, plasma medicines, and even improving on the fusion power we are having today for the maximum supply. Okay, nuclear uh, you know powers. Okay, so this is about the first slide. Let me quickly, because we are in the introductory aspect of this lecture. So now, okay, uh, we understand the concept of plasma conceptually. So let's look at the fundamental characteristics, that mathematically and physically distinguish plasma from the natural gas. There are three major criteria here we will discuss. Number one, if we talk about the Debye shielding, we talk about plasma frequency and the quasi-neutrality. Okay, these are the three major criteria we will discuss. All right. So the Debye shielding. Uh, let's talk about the Debye shielding the first case. So supposed we introduce a positively test charge into a plasma. You understand the meaning of test charge, right? In the previous lecture. So what happens if we introduce this positively test charge into plasma? Okay. Because you remember free charge particles are mobile. So the mobile electrons are attracted towards the positive charge, while other positive ions repel. So this forms a shielding cloud around the test charge. You understand this phenomena? Okay, very well. So as a result of this, beyond a certain characteristics distance, the electric potential drops off exponentially, meaning the test charge is effectively hiding from the rest of the plasma. So it involves like a kind of shielding, is covered. Let me put it this way. So we quantify this shielding distance as Debye length. Okay, you have taken note of this. So the expression for the Debye length is given. Okay, the lambda, which is equals to epsilon naught k t over n e square. Okay, so higher thermal energy in the case of temperature cause particles to move faster, making it harder to cluster them, which normally or subsequently increase the lambda. You get this point. So you have to take note of this formula clearly so that you can express your terms. Secondly, high electron density. On the other hand, it gives us more particles available to screen the charge, so resulting in smaller Debye lengths and stronger shielding. Okay, So take note of this. This is the expression as I mentioned. So the second one is the what we call a plasma frequency and the oscillations. So next, what happened when we disturb these states? I mean the equilibrium states. This brings us to plasma frequency. Okay, so this leads us to plasma frequency. All right. So imagine displaying a slab of electrons relative to to a background of heavy stationary ions. The charge separation immediately creates an electric field that pulls or pulling those electrons back towards their equilibrium states. Okay. However, so because the electrons have inertia, okay, which we regard as this ME, the electron inertia, okay, they overshoot the equilibrium mark or states, thereby the electric in that way the electric field then reverses and pulls them back again. So this creates a kind of a collective and the natural oscillations known as plasma oscillations. All right. So the characteristic angular frequency of this oscillation is given by an expression here. All right. So this fundamental frequency forms the baseline for almost all wave interactions and high frequency electrodynamics in plasma. Okay. And number four, a quasi-neutrality, as I mentioned. You know, on microscopic lengths or scales, that is dimensions much larger than the Davy length, you know, are greater than the Davy length. Okay, so L is greater than the lambda. So the total number density of positive ions, that is the Ni, is subscript is virtually equal to the number density of electrons. This relation is very important. You have to take note of this, and is equals to what the net charge density rho, which is approximately 0. So local charge imbalances can exist, but only on scales smaller than uh, comparable to the Davy length, as we clearly shown here. So this is microscopic neutrality, and you can see the separation between the electrons and ions as we shown from here. So there is a stable state in terms of the local charge separation uh, only within the a particular length, that is the Davy length. Okay. Now, uh, okay. On this, let's quickly round it off. With regard to this plasma oscillations, if electrons are displaced from their equilibrium, as I mentioned, an electric field is created, pulling them back, which somehow resulted in the oscillation that plasma within that plasma frequency. So this is what we are showing here. So Davy shielding limits electric field to what? A short distance. Whereas plasma support neutral oscillations at frequency, a quasi-neutrality, while quasi-neutrality holds a large scale, while oscillations describe the dynamic response. Okay, what I'm saying in essence here is just a summary of what I have explained previously. This Davy shielding restricts electric fields to short spatial distance, whereas quasi-neutrality holds everywhere within the microscopically step or stage. Okay, and the last case, plasmas naturally oscillate at their own characteristic space, and that's what we call plasma frequency. Okay, so let's quickly move to this is where we are now. All right. Okay. Where is this? What happened? I'm trying to move back to the slide number 3. Okay.